Okay, so chapter 4, suspension, types and parameters. So last week we talked about the purpose of suspension, different configurations of, springs and dampers, very much focused around those things. And this week is actually looking at different configurations of suspension systems and the parameters that are important when trying to tune suspension. Okay, so let's let me just close that window. Let's check. Yeah. Okay, so chapter 4, parameters. Let's there we are. Right. So the first, start off with a brief introduction, and then talk about different suspension types. So rigid axles, semi-rigid axles, and then independent wheel suspensions. Different types of independent suspension, and then the third part will have a look at some of the parameters around suspension systems. Those that are dictated by the chassis or the vehicle design, and are generally fixed at the time of design. And then those parameters to do with suspension that are sort of adjustable, after the fact, or sort of if you think about in a race car situation, the sort of things you might be able to adjust in the pits, in a sense. So so that's so we'll start off with rigid axles. And rigid axles basically mean that the wheels on each side of the suspension system are connected together. They're coupled to each other. Okay, and so you can imagine a solid bar between the left and the right side, and on the end of the bar, in a sense, is the wheels. That's a rigid axle suspension system. Okay. Obviously, some of the downsides of that is that what happens on one side of the car will impact what happens on the other side. Okay. They're it's used quite often in commercial vehicles because they're quite a sturdy design. It's very straightforward and simple to understand, and you get obviously a solid bar. It's quite like I said, basic and sturdy. You get relatively high ground clearance. You don't need to worry too much about obviously it depends if you've got a differential and stuff, but you can obviously have an axle there that's in line with the wheels, the center line with the wheels. Relatively high ground clearance. Some off-road vehicles, you can even use like portal axles where the drive shafts and the differential are set above the center line of the wheels, and then you have a gear train or something within the hubs of the wheels to drop the wheels down. Okay. Often rigid axles can be used with leaf springs. Okay, so like I said, quite an old-fashioned setup would be to have a solid axle with leaf springs and some additional linkages. And I guess that used to be quite common. Not so much now, but and in motorsport generally, they're not part of motorsport except drag racing, where the sturdiness is important, and obviously they have very, very straightforward, simple suspension, where you've got it's a great big differential and short drive shafts to the wheels. And also NASCAR, they're part of the mandated sort of vehicle design of the NASCAR. Is just have a sort of straightforward solid axle between the two. And in neither of those categories of racing, the benefits of independent suspension are not really not taken advantage of. Both use either very, in the case of drag racing, you've got a straight, flat track, and in NASCAR, you've got obviously generally ovals, and those sorts of racing setups, independent suspension, or the benefits of using independent rear suspension or semi-independent suspension are not really that useful. So that's why one of the other reasons why they're used in those categories. So here's some simple configurations or schematics of suspension. So the first picture there is your simple rigid axle with leaf springs. Okay, that's what you can see where the two are the leaves. Item one is the solid axle, and you can see that the leaves are supported at either end onto the chassis. Okay. Then the second one here is I think that's called the Watts linkage, where you've got you can see that item 6 that's supported on the chassis, and that gives a location to the center of the solid axle, and then 5 gives you a bit more lateral control of axle twist. Okay, where the in terms of how the axle is controlled as it goes through its motions. Okay, and 6 will give you the support just for left and right lateral support of the axle. Okay, and then the item 7 is another configuration of rear solid axle suspension. I'm just trying to remember what that one's called. It's in the notes. So just find it. That one's called Panhard Rod. Yes, of course. So that's the so again, item 7 there is the thing that gives control to the lateral motion of the axle, and then obviously items 3 will control how it moves under deflection in terms of what's controlled. So you can see that 3 and 7 are all connected to the chassis, and like I said, that just basically tries to maintain some sort of control over the motion of the axle. You can see how the first picture with the leaf springs, you've got very little control about what happens to the axle, except it's all based upon what the leaf springs do. Whereas 6, whereas the middle and the picture on the right are all adding a bit more control as to what happens with the axle. So here's a simple what's linkage setup. I can't remember what that picture's from. It's just generic. I'm not quite sure which vehicle that's from. But you can see that you've got the solid axle. So this is actually a vehicle that's got front wheel drive or something, because there's no drive train shown here. But like I said, there are plenty of modern cars that have some sort of have a sort of solid rear axle that aren't that axle is not based around the drive shaft. You look at a lot of perhaps front-wheel drive light commercial vehicles like a Ford Transit and stuff like that. They'll often have a solid rear axle, even though they're not rear-wheel drive. So and they have a setup not dissimilar from this sort of setup. And you can see that this blue item is the Watts linkage, and you can see that will be joined up to the chassis to help control the lateral motion of the vehicle of the axle. Okay, so the advantages: simple and sturdy design, low cost. You get a relatively high roll center, which in some can be an advantage in some cases. You've got generally high maximum wheel lift and like I said, high ground clearance. You'll often find lots of off-road vehicles, certainly sort of those that are designed for off-road racing and those sorts of things will have a solid axle, partly because of these reasons. Okay. But obviously, one of the downsides is the fact that what happens on one side of the car affects the other side, and that's an impact in terms of ride as well as handling. By nature of the fact that you've got this bar connecting both sides, you've got quite a high unsprung mass, because that whole axle from one wheel hub all the way to the other is all part of the unsprung mass, and the more unsprung mass you have, it's worse in terms of ride and handling. You need quite a lot of installation space. You obviously have the space for the whole axle to move, so you can't have a chassis that drops below the axle in the middle there. Obviously, you need quite a lot of space. Again, not an issue with light commercial vehicles, but obviously more problematic in regular conventional cars. And you've got virtually no control over the kinematic factors. Okay, so things like as the suspension deflects, you can't control the camber. There's no camber recovery. You can't affect those sorts of things. And the axle will generally be parallel. Assuming you've got a flat road, the axle will be parallel to the road, irrespective of what the body motion is. So there's obviously some issues around control of the kinematics as the suspension moves. Okay, and those are the problems with rigid axles. And like I said, generally conventional road cars don't have rigid axles anymore. And that moves on to what's known as semi-rigid axles. So this side, you've still got the coupling between the wheels, but there's some compliance between those each side. Okay, so the coupling's not rigid. So although you've got coupled wheels on both sides, because of the compliance in the system, the deflection and the movement of each side, there is some compliance. So often that will involve some trailing arms, okay, and generally you've got a coupling connecting the two. So when you hear about a car having like a torsion beam rear suspension, that's what this sort of setup is, okay, or twist beam axle. And so if I talk about the cost, on lots of cheaper front-wheel drive cars, they've got this sort of setup. So you look at a sort of Ford Fiesta type size vehicles, they'll use this sort of setup on the rear end, and even sort of mid-size hatches as well. And you can get quite good performance if you look at you obviously often hear about things like the Focus ST and the Golf GTI and that stuff. They've got multi-link rear ends. Well, often the lower spec versions of those cars actually have a twist beam axle, and even high performance hatches like the old Civic Type R had a torsion beam rear axle, had this sort of setup, and that at one point did hold the Nürburgring lap record for a front-wheel drive vehicle. So, like I said, you can get adequate performance out of this sort of setup. And in terms of because of the way the vehicle's set up, you've got quite good lateral positioning and bracing, because these things have to be quite strong. So here's a schematic. So you've got two independent arrangements, both sort of trailing arms. So you've got these trailing arms, which are item 1 on both of these pictures, and then obviously one type is just to connect simply to connect both sides with like a torsion or twist beam, and then the second type is where the twist beam is actually about way down the length of the trailing arms. And if we show a picture of this, so this is actually a rendering from a real vehicle. You can see you've got these points here, which is where that's fixed the axle, okay, with those three studs, and then they're both trailing arms, but they're connected together with this sort of beam between the two. And clearly, you haven't got independent suspension here, because obviously what happens on one side will be transmitted across the axle to the other side. But like I said, because of the shape of this and the size and the fact it's hollow, there'll be some compliance between the two, so you get sort of a little bit of independence. But like I said, this is a very simple setup for rear suspension that's been used many times. Okay. So yeah, as I said in the notes, despite this mutual wheel influence, like I said, the Megane RS 275, the Honda Civic Type R, are two examples that use this sort of setup, and to good effect in a sense. Advantages: low installation space requirements, so obviously great benefit in small road cars. Low on sprung mass, because that, unlike a solid axle, this sort of thing can actually be relatively light. Like I said, the central beam will probably be hollow. Easy assembly and removal, because you just unbolt the dampers up here and the mounting points. You can move the whole thing in one go. Low cost, partly due to economies of scale. You've got the stabilizing effect of the coupling profile, and low track width and toe angle changes, and good anti-dive properties. So you can set up the motion to deal with dive and squat. But obviously, if you've got this mutual influence, it's not generally suitable for driven axles. You'll hardly ever find a driven axle that's got this sort of setup. You've got some high stress points between the trailing links and the coupling links. So, like I said, if this whole setup, to induce the twist, you need strong joins here, because obviously there's going to be some high stress points and high deflection there. And like I said, because you've got the trailing arm basically set up, you've got not much control over kinematic properties. As the body rolls, the wheel will roll as well within line with the body. And that's sometimes that's not desirable. Okay, so that's basically rigid suspensions, semi-rigid and rigid. but then we can move on to independent suspension. This gives a lot more freedom in terms of how the kinematics are controlled and how the vehicle behaves. Okay, an independent suspension is simply defined as that each wheel is individually connected according to the desired degrees of freedom. So obviously, what I mean there is that for non-steered axles, you've got a deflection up and down. Sometimes that up and down motion can actually induce different amounts of toe. We'll talk about what toe is in a minute. But generally there's one degree of freedom. Obviously, for a front or a steered axle, you've got a second degree of freedom, which obviously allows the front wheels to turn in terms of steering. So I've said here, front wheels 2 degrees differences, rear wheels 1 degree of freedom, and that's clearly for vehicles that don't have any element of rear wheel steering, and that's becoming more and more prevalent nowadays. But certainly in large vehicles where having a bit of rear wheel steering can certainly improve in terms of manoeuvrability at low speeds and stability at high speeds. So there's lots of cars are now coming with some sort of active rear axle in terms of steering. But generally, 2 degrees of freedom at the front and 1 degree of freedom at the rear. And the arrangement of the links between the chassis and the vehicle and the wheel up between the sprung and unsprung mass is sort of determined. That determines how the wheel moves in relation to the chassis, which is what's known as kinematics. And there's lots of different types of independent suspension. We'll cover some broad types here for you to have a look at. Okay. But in terms of advantages and disadvantages of independent suspension in general, obviously there's no connection between the sides of the vehicle, so there's no influence of what happens on one side to the other side, unless you've got an anti-roll bar. But let's skip over that for the time being. As high opportunities to optimize the kinematics, how the wheel moves. The space requirement can be low, or it depends upon the type, but you can obviously optimize for space. And the unsprung mass can also be low, which is good for ride and handling. Obviously, the disadvantages is generally it's a more complex design and configuration and coordination in some cases, and often independent suspension is more costly, which is why on the higher spec cars you've often got independent suspension, whereas the lower spec versions might have a slightly simpler and more cost-effective setup. Okay, where performance is not as important. And I say maximum wheel lift is low. It depends on the design. Obviously, there are many off-road cars now that have got independent suspension, and they still achieve quite good axle articulation, but often in combination with some clever sort of off-road setups where with different locking characteristics and traction controls and those sorts of things. Because in the case where you've got a big axle twist, one of the wheels might be off the ground because of the fact that it's got independent suspension. So, like I said, it sort of depends partly on the design that disadvantage, but like I said, it's often can be gone around. So let's have a look at some simple and more complex independent suspension setups. So trailing arms is obviously a very obvious one, okay, where you've got a single link in the longitudinal direction carrying both longitudinal and lateral forces, okay. Advantages of this sort of setup is very low installation space requirement. It's very cheap, okay, but you've got very limited kinematic optimization possibilities. The wheel is going to move in one direction, and obviously if it's purely straight back or straight forwards, then obviously as the body rolls, the wheel will roll with the body in the same amount. Okay. You've got high stresses on the links of the mounts because obviously all the things going through that trailing arm link. Okay. And like as I said, if you've got a lot of body roll, then the wheel remains in line with the body, and often that induces adverse camber in road cars. It's uncommon in modern road cars. A car that you may be aware of, again, it's sort of before your time generally, but the Citroen 2CV had a trailing arm suspension, both front and rear, and in the front it was not actually trailing, it was leading, but it's the same sort of setup basically, where you've got a link between the body and the wheel that was an arm that moves up and down. So a schematic of a trailing arm looks something like this, and you can see that a very straightforward, simple setup. Now, one adaptation of this became the semi-trailing arm, and the big benefit of the semi-trailing arm is that it solves this camber issue with the trailing arms, because basically the diagonal orientation of the link means that as the wheel deflects, it also cambers, and that can help deal with this roll out of the corner of the chassis. As the wheel deflects, it will camber to try and mitigate some of that deflection or that camber. Okay, so you get better grip in corners, but obviously in heave, as the suspension deflects, it will also camber, and so that's often one of the downsides of the semi-trailing arm setup. So you'll often see, if you look at a vehicle that's got semi-trailing arm suspension, as it squats under acceleration, the wheels will camber in a sense. You get better bracing of the longitudinal lateral forces, so you've got 2 mounting points, you get a lot more, it's a bit more strength. And like I said, it was often popular for the rear end of rear-wheel drive vehicles, because it's sort of quite very well compatible with drive shafts and differentials, but it's not really used much anymore. Common vehicles that used to have it, things like the Ford Sierra, and including the Cosworth, RS Cosworth versions. The old E30 BMW 3 Series also had a setup with semi-trailing arm suspensions, and I think even old 911s had a semi-trailing arm setups. And so, like 1980s, basically, is when it was still popular. So there's a schematic. You can see the diagonal links there. And you can see that as the vehicle moves, as the wheel moves around the axle, because of this diagonal setup, you actually get camber at the wheel as well. And in terms of a real vehicle, this is the back end of a 3 Series, I think, yeah, E33 Series, and you can see that this trailing arm mount, rear axle carrier, that will be fixed to the chassis. Okay, and the trailing arms are actually mounted upon that, and you can see that because of this diagonal setup, that you've got a semi-trailing arm setup. You can see that this is the drive shaft coming through to the differential at the back, and then you've got the drive shafts coming out of the final drive, connecting to the wheels. Okay, to the hubs, the brakes and stuff. So there's your coil spring and damper as well. Yeah, and that's basically the setup of the semi-trailing arm suspension. Okay, double wishbone. This is one that you may already be familiar with, because it's often used in motorsport applications, including on the Formula Student car. So that you've got wheel connected via 2 sort of A-shaped or wishbone-shaped arm links. Okay, the suspension braces all the forces and torque, so they're taken through all the links. Okay. And then you have an additional link, a tie rod, used for controlling toe, and obviously if you've got the on the front axle or rear axle for steering, then that's controlled generally through the toe link as well. It's very predominant in motorsport due to the high configuration and kinematic possibilities with inboard springs and dampers, operated by push and pull rods and bell cranks and that sort of stuff. So you can actually position the spring and damper within the shrouded body of the vehicle, with double wishbone suspension. So they're not in the with a single seat race car. You want to minimise the drag of the elements that are outside of the body, and so obviously you can position those things inside. That helps. One of the downsides, obviously, is the requirement for space is quite high. And as a consequence, on many larger roadway vehicles, that's often where you find it at the front axle. So yeah, like I said, it depends on the size. You don't often smaller hatchbacks don't use this sort of setup because they haven't got the space, and certainly vehicles with transverse engines also tend to not use this sort of setup But if you've got a longitudinal engine position, you generally got a bit more space. So double wishbone front suspension is good. And you may follow recent car releases, and one of the key changes to the Porsche 911 GT3 for the most recent generation. One of the big changes they made is they swapped the front suspension from a strut-based setup to a double wishbone setup to match the racing cars, and obviously there's been lots of praise thrown upon the change that they made in terms of the grip and the precision and the various kinematic benefits of having a double wishbone suspension setup. So like I said, it's often on front axles of many larger road going vehicles. In fact, on my car, I've got a Honda Accord, and that's got double wishbone front suspension. So, like I said, it's sort of it depends on the size of the car, but like I said, it does happen on lots of road going vehicles. So there's a straightforward sort of schematic of it. So you've got your A arms, which are items 3 and 2. Both the top and the short are top and bottom. They could be different lengths. We'll talk about double wishbone configuration in chapter 5 actually, in terms of how you set up the kinematics and how you can deal with sort of camber recovery. But you can see there you've got 2 and 3, which are the wishbones. You've got 5, which is your tie rods, so that controls the toe, and then 1 on both sides is your sort of wheel hub and wheel carrier, and all the brakes and various other things that are stuck out on as part of the unsprung mass. So there's a schematic. I haven't got a picture here, but because we talk a bit more about double wishbones next week when we cover chapter 5. Strut base, which is what I mentioned earlier, is often similar to double wishbone, but instead of having 2 links, top and bottom, the upper link is actually replaced by some sort of sliding guide, and that's made up generally from the spring and damper. Okay, and so the spring and damper are rigidly connected to the wheel carrier, and so they not only do they control the suspension movement in the vertical direction, but they also will take some of the forces through the drive and braking and the lateral loads as well. So the lower link will be more like a traditional A-arm or wishbone design, but the upper link will be the suspension unit generally. Can be referred to as the McPherson struts. That's one of the sort of names that's been given to this suspension design. So if it says McPherson strut, it'll be this sort of design. Benefits: very low construction overhead, good packaging, low cost, partly due to economies of scale. So like I said, I would probably say most road cars will have a strut-based front suspension system. It's very, very common in many road cars. Certainly the smaller ones, and even sort of high-performance cars will have a strut-based front suspension system. One of the big benefits is the packaging. The fact that you've got a lot of space in between the axles, despite having this sort of setup. So lots of space for things like engines and motors and batteries and that sort of stuff. So very, very common in road cars. There are some fewer optimization possibilities than double wishbone. There are some you can make, but you've got less control over what the wheel does, and less ability to adjust it. So in terms of camber and roll center, you can't really adjust it to optimize those things. They're sort of quite fixed by the design. Often you need sort of quite a lot of vertical space requirement. That sort of depends on the springs and suspension you're using, but often that despite the high vertical space requirement, you've often got space in the road car to implement this sort of setup. And one of the downsides is the fact that due to the sort of front axle geometry, and we'll talk about that in a minute, in terms of optimizing, you've got this issue with spindle length and scrub radius. And if you're sending drive through a vehicle that's got a large scrub radius, you get what's known as torque steer, where the drive going through it is trying to steer the steering wheel, and so you end up with and depending on different length drive shafts and that sort of stuff, you end up with an element as you accelerate hard, the vehicle's trying to steer as you accelerate. And so obviously, well, that's one of the issues around strut-based suspension systems, because of the way it's all set up. You end up with this situation where you get quite a large scrub radius. That's an issue. So there's a simple strut-based setup. The drive's not shown here, but you've got this lower wishbone, like you can see here. You've got the tie rods, again, generally connected to a steering system or to the chassis, if it's not a steered wheel. And then item 4, you've got the spring damper set up here, and that's connected to the chassis as well. And so that provides some aspect of support in terms of the vehicle positioning of the wheel and the hub. Okay, so there's another schematic. So one of the ways to deal with the torque steer problems is to have what's known as a super strut. Okay, and it aims to solve this this sort of torque steer issue by reducing the ability to or reducing the issue around the front axle geometry. And how that works is that separates the strut into 2 major components. So here, if you go back to the strut, you've got sort of one major component here, this wheel hub carrier thing set up. Okay, and you can see that if this vehicle was steering, you get a motion around the lower wishbone point and the top of the damper. Okay, and that's the axis around which this thing rotates, and that's the thing that causes the large scrub radius. And what you do is you basically separate that single element into 2 major components. You've got the thing that deals with the up and down motion of the suspension system, the spring and damper assembly, and then you've got a separate knuckle attached to that assembly that does the steering. Okay, and the advantage of that is you can position the steering axle, that axis around which the vehicle steers, in a completely different place from where the spring and damper is assembled. And that means you can have a much more vertically aligned steering axis, which is better for various reasons. You've got much more control about how that works, and then you've got a much shorter spindle length and reduced scrub radius, which is the thing that reduces torque steer. And if you look under the front end of some hot hatches, like the Mark II Focus OS and the VXR Vauxhall Astra, and various other front end, I think even the things like the Megane RS and a Honda Civic Type R and those sorts of things, they've got this sort of super strut setup. Okay, and so a schematic of that is here. So what you've got on the right there is the conventional strut, and you can see that the steering axis is between the top end of the spring damper unit and the lower wishbone sort of mounting point. And that whole assembly, so you've got the assembly that's shaded in white there, is your whole thing that rotates when the vehicle's steered. Okay, so that's the steering axis. You've got quite a high spindle length, which is the distance between the sort of steering axis and the center line of the wheel. Okay, oops. And obviously you've got the scrub radius, and so you can see that because the center line and the steering axis are not in the same place, as the vehicle drives, as you put drive through that wheel, it's going to want to steer. Okay, because it wants to rotate around so that those things are in line, and that's obviously the thing that gives you torque steer. And depending on the length of your drive shafts and stuff, often in a front-wheel drive car they won't be equal. You end up with a steering influence on the drive shaft. Now the super strut, you can see that basically separates. So you've got this red item shaded in red, which is your thing that deals with the springing, the up and down motion. Okay, but then there's a separate knuckle, which is the item in green, which does your steering. And you can see that the front, or the top of your steer axis is now right inside the wheel hub, as opposed to out here on top of the chassis. So so you can actually much more minimize the spindle length. Okay, that distance between the steer axis and where the wheel, or the center line of the wheel, and you can see the scrub radius has been massively minimized, so you can make them intersect. Okay, often they don't intersect because you actually want a bit of feel through the steering as to what's going on, but you want to minimize the impact on the steering. And so you can see this is the sort of setup that's been designed to deal with the issues of a strut-based setup. So you've still got the big benefits of packaging and stuff, but you've got much better control of the steering as part of that setup. So like I said, when you hear about hot hatches and or with, like I said, with the Ford, the Revo knuckle, that's what this is talking about. The fact that you've got this Super Strut design. Okay, and the last type I'll talk about is what's known as multi-link. Basically, that's sort of any suspension, independent suspension setup that doesn't sort of fall into the previously talked about categories. And so multi-link is where you've got many links, and you know, imagine if you broke the double or you broke the wishbones of a double wishbone suspension, you start to get more than one link or more than two links. And that's a example of a multi-link setup. You've got loads of possibilities in terms of configuration of multi-link suspension systems, and obviously each of those comes with benefits in terms of the kinematics. They can exist at the front and the rear end, and they're often common on road cars at rear axles. And like I said, many road cars have a multi-link rear axle. Certainly from sort of mid-range sort of family hatchbacks to all the way up to much larger vehicles will have a multi-link rear end due to those aspects of configuration. In fact, I used to have an old car that had a multi-link rear end, and they actually marketed one of the aspects of the marketing was around this the fact that the toe has sort of had an element of passive rear steer. So as the wheel deflected at the back, you end up inducing a certain amount of toe, which helped with handling. And that was due to the fact that you had these different links of different lengths, and as the thing deflected, it would not only control the motion of all the camber of the wheel as it moved up and down, but also the toe angle. And like I said, that's sort of one of the things that you can do. So there's the schematic. You can see there's lots of different links. All those links are identified as item 2, one being the wheel carrier and wheel. And there's a schematic. I can't remember what car this is from, but you can see there's lots of different links there being shown up. It's just a rendering, and you can see. So you've got these. You've got sort of trailing arms. You've got these sort of links that come out from the centre of the wheel. Like I said, controlling how the wheel moves as it moves up and down stuff. So you as a typical multi-link setup. Like I said, there are lots of benefits to this sort of setup in terms of configuration. Okay, so that's suspension types. We're sort of racing through this session. Are there any questions at the moment? Okay, no questions. Okay, that's good. Yeah, so the sorts of questions you might get asked about this at the end of the chapter in the notes as that gives you a sort of flavour of what you might be asked. So if I just have a look at those, so if I go. So some of the example questions. Okay, explain in your own words why rigid axles are not generally used in motorsport applications. Are there any exceptions, and if so, why? There's a sort of clear sort of question, and obviously the answers are in the notes. What are the benefits of semi-rigid axle over fully independent systems? Giving a full explanation, what aspect of the semi-trailing arm suspension aim to improve over trailing arm? We talked about that. It's about the camber recovery. Discuss the benefits and limitations of a strut based suspension system, making comparisons to the more expensive double wishbone suspension system. So obviously, you look at the disadvantages of a strut based setup, compared to double wishbone. And then how does the Super Strut differ from a standard strut, and explain the differences that help minimise torque steer. Again, sort of, there might be questions around like drawer design. What are the drawbacks of a double wishbone suspension? So these are the sorts of things that might be asked around these sorts of questions. Obviously, one of the in terms of the assessment this year, you'll have access to your notes, so you can imagine that those questions might be altered somewhat to accommodate for those things. Okay, so let's go back to the presentation. Okay. Okay, so moving on, let's talk about parameters. Okay, and so like as I mentioned at the beginning, there are some parameters that are part of the vehicle design that are very, impossible to adjust sort of after that design stage. And these things are quite fundamental to how the vehicle responds to inputs. But like I said, there's the sort of things that are quite tricky to adjust after that design aspect. And the first one of those is obviously the position of the center of gravity. Okay, and so that's the center of gravity of the whole vehicle, certainly of the sprung mass, and often that's defined through basically distances between the axles and the height from the ground, and there can be some assumption around the fact that that puts probably on the center line, but like I said, that may not be the case. But yeah, measure distance from the front axle to the center of gravity and the height from the ground. Okay, and basically, if you're doing sort of lump mass modeling, then that's the point mass of the sprung mass of the vehicle. So that's all centered around that point. Okay. Clearly, there's a front-rear distribution. We talked about that when we were looking at, certainly in chapter 2, when we were looking at vehicle cornering characteristics and stuff. And depending on that front-rear rate distribution, can significantly impact the handling balance, as we saw often with a front bias, so more weight on the front, that leads to sort of understeer, and rear bias will lead to vehicles tends to oversteer. And obviously, you position it near the middle, you've got sort of neglecting a whole bunch of other aspects. You're going to end up with something that's more closely going to be a neutral steering vehicle. As you're probably aware, BMW often touts the fact that you've got 50-50 weight distribution front to rear, and that's obviously part of the sort of marketing message around the sort of handling of something like a BMW. It's the benefits of having the 50-50. The height obviously will affect the pitch and the roll motions, okay, as well as load transfer. If you have a high center of gravity and a low roll axis, then or pitch axis, then you generally have quite a high roll moment due to the center of gravity position and the height, okay. And so obviously you generally want it to be quite low, but you don't want it below the roll axis. We'll talk about roll axis next week, but like I said, that's one of the things that would impact how much the vehicle roll. And like I said, yeah, you generally want it to be low, the center of gravity. One of the reasons why some of the benefits of a battery electric vehicle, where you've got this sort of skateboard set up or sled set up, where all the batteries are mounted, right down low, gives you a low center of gravity, and so that can lead to more, slightly more desirable handling characteristics of the setup. Clearly, another design aspect is the wheelbase. Okay, so that's the distance between the front axle and the rear axle, the center points of those positions, and it has a big impact on the load distribution in conjunction with the center of gravity position. Because, like I said, you measure the center of gravity as the distance between the front axle and the center of gravity. Obviously, there's the corresponding length of the rear, but obviously the long wheelbase would be largely more stable and less agile, whereas the short wheelbase will give you more instability, but more agile. Okay, so the length of the chassis makes quite a big difference. So linking that to Formula One, you've got the difference between, say, last year's Red Bull and last year's Mercedes. Mercedes had a much longer wheelbase, and was gave very good performance in long, wide radius sweeping corners, whereas shorter radius, slower speed corners often benefited the Red Bull because of the more agility that they got with the smaller wheelbase. This year, wheelbase has been curtailed, to a certain extent, they're going to be more in line with each other. The 2022 regulations. Obviously, there are many other differences, things like brake angle and stuff. But wheelbase is one of those aspects as well. We also look at rally cars. Often the smaller rally cars there's more instability and more instability, but more agility. it's longer motor vehicles. Okay, so track width is another sort of design aspect, and the lateral distance wheels each. Okay, so you the left and the right, you measure the center line of the wheels, how far apart they are across the track, and that will be a design aspect. And that has an effect on corner performance in conjunction with centre of gravity. Next week, when we talk about roll, you'll see that track is one of the things that, the value P is one of the things that impacts how much the vehicle rolls in the corner. And generally, wide tracks reduce that load transfer across the vehicles, and it's generally desirable. Clearly, there's an impact on the vehicle size about track width. Again, look at Formula One regulations in the early 2000s. You had a maximum width from the outer edge of the tyres of 1800. That went up to 2000. I don't remember when that was, but it was either the late 40s or the early 2010s is when they put them back up to 2000, which is what they were back in the 90s and the 80s. So wide tracks reduce that load transfer because the axles. So that's the sort of design aspects that impact your center of gravity. Sorry, that impact your vehicle performance, and they're the sort of things you can't really change after the fact. Okay, it's part of the design. So those are the things that need to be considered when designing a vehicle. And then these are the things that are directly associated with things that often are adjustable, can be tuned after the vehicle design. So these are, can be tuned to give vehicle damage required by the engine application. The ability to adjust these parameters at the track side is quite important. Okay. It can depend on what the driver prefers, rather than what may give the outright performance the perfect ideal driver. So, different drivers prefer different types of handling characteristics. These are the things you can adjust. If a driver prefers like a really unstable, more sort of oversteering type chassis setup, another driver of the same vehicle, then you can obviously tune the vehicle to give you those sort of characteristics based on some of these parameters. So the first one we'll talk about is toe. Okay, so that's measured how far inward and outward the leading edge of a tyre is facing when viewed from above. So you're looking down the vehicle and you've got other wheels in line with the vehicle. Well, do they toe out, in which case they point out, or do they go in? And there's quite an effect on how the car reacts during inputs and same thing. So here there's a plan view schematic. So you can see the toe in is where the wheels are pointing slightly in towards the center line of the vehicle, and toe out is where they point out. Okay. And like I said, these are the things that impact in terms of corner and exit. So the amount of toe affects stability. So straight line, you want no toe, you want to minimize the toe. For entry handling, the toe out the front will encourage the initiation of toe and make the steering slightly quicker, and contributes to an oversteer. If you've got toe in, that leads to oversteer. Okay, so like I said, there's a balance to be struck what the sort of what the driver wants, and the toe out leads to oversteer and a bit faster turn. So these are the sort of things that toe in enhance traction out of the corner. So sort of in a sense exit handling. Okay, so like you want a bit of bump in the sense. It's obviously is balanced with tyre wear. If you've got no toe, that's obviously better for tyre wear. Having some toe will give you more unbalanced tyre wear across the width of the tyre, either leading edge or trailing edge wear, and more than the other side. As associated with this, toe in leads to front oversteer. The front leads to understeer. Generally, road vehicles are set up to understeer because it's more straightforward to control, and so that's why street cars are generally set for a bit of toe in at the front to give you that understeer, and conversely, racing cars will give you a bit of toe out. Now, you may remember at the start of last year in the Formula One, there was this stuff about Mercedes using this, what do they call it? DAS, Direct Access Steering or something. I can't remember what the D stands for, but something access steering. And you saw during testing that Hamilton and Bottas were pushing the steering wheel in or out, and that was adjusting the toe of the front wheels. And what they developed is a setup where by moving the steering system in and out, that would move the rack of the steering in and out, which would then actually have an impact on toe. And the way they designed it is they set it up so that in a corner you'd get a bit of toe out, and then along the straights you wanted to minimise toe, so you could actually push the steering wheel in, and you'd all put it out, and you get the toe would adjust, and you'd see the vehicle. Obviously the straight line stability would be improved, and then as you braked into a corner, toe out that you wanted. And so, like I said, so that was one of the things where they tried, an attempt to try and deal with this mismatch of characteristics and what you wanted. So that's one of the things you can do. Although that system is now banned for this year, but like I said, it was something that they did investigate last year. Okay, one of the most important aspects in terms of vehicle handling is the camber angle of the wheel. Okay. And that's the angle of the wheel relative to the vertical. And this has a big impact on the dynamics of the vehicle. Okay. So camber angle, looking at the picture, so negative camber is where the top of the wheel leans towards the centre of the vehicle, and positive camber is where it leans out of the vehicle. And in terms of which direction you want it, it depends on what's going on, really. And the other sort of impact here is something called camber thrust, because you get what's known as coning of the wheel. Okay, so you can see that if you've got negative camber, the way the wheel actually interacts with the ground is you end up with a slightly conical shape to the tyre, and that will actually provide you some additional cornering forces as well as the wheel turning. So that has an impact here. So, like I said, the cornering force is highly dependent on the angle relative to the road surface. Okay, the tyre develops maximum lateral force at a small camber angle. So obviously, large camber angles, you're going to reducing the ability of the tyre to make cornering forces. But small camber angles can help. There's a camber thrust, so like I said, literal lateral load. So you'll notice that when you're riding a bicycle or a motorcycle, the actual steering inputs are quite minimal, and you're generating most of the cornering force through camber of the tyre. Obviously, motorcycle tyres and bicycle tyres are designed to camber, so how the whole thing works. But like I said, you can actually induce a bit of camber thrust from road tyres as well, or road car tyres, and so you can have additional lateral force being applied through camber. Okay. Generally, the way vehicles are set up is to have a small amount of negative camber on the outside wheels in cornering. Okay. Because what you essentially want, if we go back to the picture, you want this additional lateral load to be on the outside wheels, because they're the vehicles that have most of the vertical load. Okay, and to give this additional lateral bit of camber in the corner is a big benefit. And you want the top of the tyre to point towards the centre of the corner as the vehicle is going around to give you that camber thrust. Adverse camber, which is where the wheel points outside of the corner, is bad because it gives you less grip, and you've got a cornering forces in the opposite direction due to that camber thrust. So you want a little bit of negative camber, okay, but obviously that must also be balanced with wear on the tyre. As I mentioned, if you've got camber, then you're going to have wear on the inside of the tyre. So a small amount of negative camber. The other aspect of negative camber, and we'll cover this more next week, is the fact that if you set a vehicle up with negative camber in the first place, as the vehicle body rolls out of the corner, that negative camber can be sort of accommodate that roll and still end up with either zero camber or a little bit negative camber as the vehicle body rolls. So like I said, you need to camber the wheels slightly in. Obviously, that could be taken to extremes. You end up with these cars that have been stanced, where you've got some ridiculous camber. Again, have a look on YouTube, but there's lots of images of camber cars with ridiculous camber angles. And in fact, one of your colleagues, somebody who was doing motorsport performance a number of years ago, had I think he had a Vauxhall, the Volkswagen Jetta or something with ridiculous camber angles. So you see vehicles like the one I'm about to show you here. So let's go back to where am I? There I am. So if I stop sharing this and share. So Google search. So you see these sort of ridiculous setups of vehicles with ridiculous camber angles. I mean, that just looks broken, isn't it? You can see that, yeah. Obviously, one of the big issues with this, and this is reported by the student who had a Volkswagen Jetta with a similar setup, was the fact that the tyre wear was unbelievable. You just got this pattern. And obviously, it also ruins handling and stuff. Engineers spend millions and millions of pounds optimizing handling, and then it gets ruined by people who do this sort of stuff. Anyway, so take your choice. Anyway, so balance with tyre wear. Okay, so that's camber angle. Caster angle is the angle made with by the line connecting the upper and lower steering pivots and the vertical reference line. Okay, so if you look at the side of the vehicle, and there's a line through which the steering or the toe is adjusted. Okay, and obviously the vertical reference line, and it's used in the front wheels, but can be on the rear wheels for motorsport applications. Certainly, if the rear wheel has some aspect of toe control, as the wheel deflects, there'll be a caster angle involved there. Okay, positive is inclined rearwards, negative is inclined forwards. Most setups have a positive steering angle because it brings benefits in terms of steering feel. And if you think about bicycles and motorcycles, they also have a positive caster. And that's basically where the steer axis is in front of the contact point of the wheel. Okay, and so you end up with this caster setup. Negative caster is quite an unstable setup. And like I said, I'm not sure of any actual vehicles that have negative caster. There are a bunch of cars that sort of had almost zero caster angle, and they had interesting steering characteristics because of that. But like I said, yeah, most vehicles have a positive caster, and that's what causes self-centering. So as you apply lock on a vehicle stationary, and then you pull away, the wheel will unwind itself because of this caster aspect. And likewise, if you apply lock and then start backing up, or you don't apply any lock, or apply just a little bit of lock, start backing up, the steering will actually wind itself up, because that's where you've got negative caster. Okay, so like I said, generally undesirable to have negative caster. It's more desirable to have positive caster because it gives you that steering feel. Really, very big positive caster will be quite lazy and heavy steering, whereas a much smaller caster will be more agile and less lazy, more immediate. Like a zero caster angle, one of the issues with that is you don't get any of that self-centering as the vehicle pulls away. There's no steer axis, there's no self-centering tendency, there's no steer of torque being generated. And so, yeah, like I said, that's often not featured. There was a car in the 70s, the Citroen SM, which is quite an unusual car, that had zero caster at the front wheels. But they actually had an interesting setup. A lot of things were hydraulically controlled in that vehicle, including the pneumatic suspension. But they also had active control of the steering. And so instead of relying on caster to provide the self-centering, they used the hydraulic system to actually generate the steering there. So you could actually the vehicle, when stationary, can actually steer its wheels by using the hydraulic system. So, like I said, it was an unusual setup, but like I said, that's often positive caster is used to deal with that aspect. So, like I said, contributes to steering feel, helps in the terms of self-centering. Large trail will give you heavy steering and a strong self-centering tendency, but a short trail, so that trail is the distance between the contact point of the tyre and the intersection of the steering axis with the ground. That distance there, so here, in the positive caster, that distance is in front of the contact point. Okay, that also indicates not only is it the angle, but it indicates that distance. So large trail gives you heavy steering and strong self-centering. Short trail will give you lighter steering, but poor self-centering. Like I said, positive use of most, if not all cars. I'm not aware of any that have got negative. And positive caster gives good camber steer relationship. So likewise, as you steer the wheel, because you've got that caster angle, you actually get camber of the wheel as well. So if you look at I don't know whether any of you have certainly on things like BMWs and Mercedes, they often have quite a large amount of caster steer. So if you see a car parked up with the wheels on full lock, you'll see that the wheels are actually cambered in and out of the as well. So that again, that generates, as the vehicle body rolls, you get benefits in terms of camber angles. I don't know whether I can find a picture of what I mean. Let's have a look. So if I go from look. The sort of thing I'm talking about is let's have a look. Try. Yeah, let's better search. Let's go to this one. So the sort of thing I'm talking about is this picture here. So if I go back to Club Gate, stop sharing. Like I say, Google is your friend if you want to find examples of this cool stuff. So here we go. So you can see this this one that I've highlighted there. You can see that as the vehicle turns on the lock, you've got a bit of camber. And likewise, if we go down to the BMW, you can see it on this picture of this drift car, where it's quite extreme. So you can see there's a camber being induced by the steering angle. And that's due to the caster angle of the wheel. So again, it's the same sort of thing. You see that sort of, there's an additional angle being generated by the vehicle when it's on lock. Pictures. Oh, there it is. There's caster angle. There we go. Confirming there's another drift. You can see there's big caster angle. They've obviously had some suspension modifications to get a steering angle that wide. Say that sort of drift. Just as an aside, if we go back up, I saw a picture of a car. I wanted to show you this. Back in the, I think this is the 70s or 60s even, 1960 Milliken MX-1 camber car. So this is a vehicle, a racing car where they actually, you've always got motorcycle tyres, and all the wheels have got this massive camber on. And the idea behind that, the benefit was around the fact that you've got large amounts of lateral force being generated. Obviously, in a straight line, they were counteracted by each other, but in the corners, when there's most load on one side, you've got additional cornering force like you would in a motorcycle. So, like I said, that's a particular example of a car with a ridiculous camber that actually was used as part of that sort of thing. Anyway, so let's press stop. Go back to the presentation. Okay, Kingpin Geometry. Okay, so this is about the axis, the angle that the steering axis makes vertical with the vertical plane of the vehicle when viewed from the front or the rear. So going back to that Super Strut picture, that's sort of showing you some of the Kingpin geometry. Okay, and like I said, when it's towards this vehicle center, which almost it always is, that's called positive Kingpin geometry. So here we're looking at the axle of a front axle. Okay, so again, you've got like some sort of strut-based system where you've got a lower wishbone, lower ball joint down here, and then if you've got low front, like a wishbone at the front, then it would come in at this upper ball joint low, and then obviously high if you've got like some sort of strut-based system. So you can see the spindle length is the distance between the steer axis and the center point of the wheel. Okay, so that's the distance there. Okay, you've got an angle, Kingpin inclination angle. Okay, wheel offset will be the sort of point of the wheel where, from the center point to where it's actually bolted onto the hub in a sense. And then you can see in this setup, the way it's been designed is you've actually got a negative scrub radius. So the center point of the wheel is actually inside the steering axis. So again, that also will generate torque steer because it's non-zero. Okay, but the way this is set up is you've got this set up over here, and obviously clearly the inclination of this angle will change this distance here. Like the caster does. But the closer this is to zero, the more likely this is going to be reduced and in line with the center line of the wheel. Okay. And that's one of the things that the Super Strut enables you to do, is to reduce that Kingpin inclination angle. If I go back to the Super Strut, which is over here, there it is. You can see that this angle, the steering axis angle, with respect to the vertical, is massively reduced compared to this axis, and the angle center line. This angle between the dash dot line, the center line, and the blue line here is considerably bigger than on the Super Strut design. So, like I said, one of the effects of the Super Strut is to reduce that steer axis angle. So like I said, this is also very important to how the vehicle behaves. And again, it's one of those things that if you look at a steered wheel, a front wheel on full lock, is where you can see some of the impacts of this geometry. Okay. So it affects the spindle length. Okay. Positive will cause the vehicle to raise up when steered, and it causes positive self-aligning. So that's another aspect. So as you apply lock, the vehicle will actually, because of the position of the tyres, will actually raise the suspension up. And you end up going with a slightly, and obviously one of the things that does is the gravity affecting on the sprung mass will push down, which will try to unsteer the wheels. Okay, so you get this self-aligning effect, which obviously is a benefit. Affects steering camber. So as you steer the wheels will camber. Against that Kingpin inclination will affect that. So when the wheel is turned, it will lean out at the top towards positive camber if the Kingpin inclination angle is positive. So like I said, as you steer, say to the right, the wheels will actually naturally camber to the right, which is a benefit because they're sort of negative camber with respect to the corner. And obviously that gives you a better grip. So obviously that's also a benefit. And it affects the scrub radius. Like I said, the steering, steer torque or torque steer, as you apply power through those wheels, you want to minimize the scrub radius, otherwise you're going to get of steering through an influence on the steering through the torque being generated in the wheels. And that's again due to the scrub radius leading to torque steer, which is, like I said, generally undesirable. Again, YouTube is your friend if you want to see what I mean by torque steer. So let's have a look. See if I can find it. So let's have a look.
this car.
Yeah, so I found an example on YouTube. Let's see if I can get it on here. Of torque steer. So there's a Focus ST that's doing it. Let's have a look at it. Yeah, there we go. So it's okay. Let's show it a second. Right. So again, these are sort of things you can look at when investigating. So it's a small video, but like I said, can you all see this? So there's it's just going to pull out and then come to a stop, and then I'll accelerate hard. And if you look at the steering wheel, let's go to the steering wheel, and you can see it starts steering to the right. Yeah, so there we go. Torque steer. Let's stop showing that. There are many more examples. Yeah, so that actually finishes the content. We're at 10 to 1, so we've got plenty of time. If you've got any questions, if not, then we can finish a little bit earlier today. So if I'll go back to stop recording.